this is me being a little bit hopeful, but I think ObjectLayout and StructuredArray is about the near future, or the near future I hope to see. We're going to try and deliver on that. And rather than looking at this as something that improves language support, well, it will, but we're looking at Java primarily as a language and other things that use it, or looking at this as something that enables us to talk to the outside world or to native code or to GPUs or to other libraries and get a full, complete picture. We're looking at something really simple, speed. We want to make Java faster, and we want to close one of the inherent gaps between Java and C on speed. That gap has to do with memory layout. So I'll talk about what I've been working on kind of as a side project for a year and some, and we've been actually working on delivering some real code for it at Azul and into OpenJDK. So what is object layout? The focus is to match the raw speed benefits that C-based languages can get out of common memory layout patterns, but do it in a natural Java idiomatic way on the heap for POJOs. So this is not about laying out some sort of flyweight on top of off-heap stuff to get fast. It's to fight the need to do that. It's to avoid the need for unsafes. It's to avoid the need for direct byte buffers over stuff just to get speed of streaming. And to do that for as natural a way as we can get for a Java programmer to use. The focus is on speed, on regular Java objects, and on the heap. None of these are the focus. We're not looking to improve footprint. I could care less about headers. I could care less about heap size. You guys know I like large heaps, and I think garbage collection is simply a solved problem. But this is not the problem. These are not speed-affecting things, or at worst, they're third-order speed-affecting things. This is not about half-heap solutions, and it's not about immutability. Every one of these is simply an orthogonal concern. I'm not saying they're good, they're bad. I'm saying I just don't care about them here. Okay? This is purely about these three things: speed, Java objects, on heap. Is there a goal overlap? We just talked about value types, which are really cool, by the way. There are also things that deal with off-heap and foreign things, like packed objects and JNR and FFI, which are really cool, by the way. But this does not overlap with them in any way. This is laser focused on a different problem, and it doesn't conflict or contradict with any of the other work. It's simply orthogonal. There's minimal overlap that does exist. We can do something in all these three things that is probably similar, but that's about the same as the overlap between an array list and a hash map. You can put objects in both of them, but they have different purposes and they're optimized for different things. Looking at it pictorially a little, because I've had a little time to hack on this while I was listening, value types are focused on these things, the way I see them. Immutable. Return values is a very strong reason I really want this stuff. On-stack behavior for this will be great. I think we'll see a lot of thread local on-stack use of value types. They'll become natural, second nature for everyone. And they can be represented on a heap, but my personal feeling is that we'll see them on the heap either as completely safe thread local things or as box types. Word tearing and anything larger than 8 bytes effectively will have atomicity issues, and we'll work on those, I'm sure, but I think there'll be challenges around speed there. On the other side, whether it's FFI or look at the packed object work IBM did, because it's very elaborate and very good, it's about precise layout control. It's about the fact that Java has to deal with things outside of Java, and those things already have decided what the layout is, and you have to deal with it, and you have to be able to spell it out. And doing it yourself with a flyweight over a byte buffer is extremely wasteful and annoying and buggy work. It's usually about off-heap or things outside of the Java normal managed heap, at least. And it's usually about sharing data with something. Object layout is about speed for Java objects on the heap, right? None of these are really a direct overlap, the on-heap part a little bit. The other way to look at it is in value types, we're talking about new code. This is a new thing you can express. You can pass it to other new code that understands this new thing. Similarly for packed objects or for FFI. It's a new thing. You will write new code that will use this stuff. Object layout is intended to work with all existing code that understand the Java object. Anything you could do to a Java object will work within this. And here's the overlap. Arrays of small footprint values are something we could probably express in all three of these things. But that's about the size of it. So this is mostly a reaction to every time I talk about structured array or object layout, people say, well, isn't that the same as? Well, right at that corner it is, but nowhere else. Okay, so what's the origin of value types? It actually started with an argument. Me and Martin Thompson were going at it on something, and this is a common argument I hear or run into a lot. It goes something like this on one side. We really need structs in Java. Look at all this stuff we have to do just to match the speed that C trivially gets out of structs and arrays of structs and all this cool streaming things. And people do this. I work with people who do all this work, and they will show me why unsafe is something they use, and they wish they didn't have to use it, but they can show you the numbers. It's just faster. And you know, they don't even use buffers and byte buffers because the range checking on them is a non-final number, and et cetera, right? So that's one argument. The counter argument is that we already have structs. They're called objects. They're even better than structs. Anything you could do with a struct, you could do with an object. What we're really missing is competitively speedy things that deal with objects for the same semantics that C has for those competitively speedy things. And right now, we're missing some of those semantics defined in a Java world. It's all about what I call enabling semantic limitations. It's about taking things away, not adding things. By chopping things down, we're able to enable optimization and speed. In C, we do it explicitly, but in Java, we can do it just by defining the semantics correctly. So where does the speed I'm looking for come from? It's primarily dominated by two factors. The first one is the ability to dead reckon to a data address. Given a containing object and something like an index or a set of indices, the ability to mathematically derive the data address I want to get to without indirection, with no dereferencing, with no data-dependent loads needed to get there. That's an extreme speed benefit for primarily for single-shot accesses. So imagine a hash table get or a hash map get. We have to do some computation and hop and hop and hop and hop. If we can take out one or two of those hops, we'll be in better shape. And CPUs in general are really good at speculating past control flow dependencies, but they're really bad at speculating past data dependencies. Figuring out what the next address is something CPUs just don't do a lot of. The other side is streaming. Streaming comes when we actually do stream through memory, usually in an array, usually by doing some sort of sequential access. And if we do that sequential access and we have a layout that is nice and flat, then we'll get predictable striding, and the prefetchers, whether they're software or hardware, will hopefully do a good job for us and basically combat latency. We'll fill the pipe with stuff, everything acts from a latency perspective as if it's already in our L1 cache. And then we're bandwidth limited rather than latency limited, and things are really good then. Here's what I mean by speed enabling limitation. Why is object array inherently slower than a struct array? What is it that makes it inherently slower? It's the fact that it's got semantics that are much wider. In Java, an array is a mutable array of same base type objects. You can replace elements, and you can have elements of different sizes in an array. That's basically the semantics of what an object array is. In C, we have an immutable array of exactly the same type, and that's what an array of structs is. The fact that it's mutable and the fact that it's variable length for elements is what requires us both to dereference and break streaming. Neither one of those qualities could be had well or easily if you keep these qualities around. So as an example, structured array, which is the main thing I'll talk about today, is an immutable array of potentially mutable but exact same type objects. It basically aims to match the semantics that an array of structs has, the ones that give you speed. Not trying to match the syntax, not trying to actually have structs, just giving you the qualities that actually give you the speed. You can instantiate it, you could do gets on it, you cannot do puts on it. Exactly the same limitations that an array of struct has. So there are target forms that in object layout we're looking at. There are 3 of them, and they're easily identified. I think that John described all 3 of these fairly well in his Arrays 2.0 talk that I saw online. It's a great talk. Anybody who hasn't seen it, it's a great coverage of the landscape of what everybody wants and what all the terms are. So I really liked it. The first one is an array of structs. We just talked about that a little bit. The other one is a struct with a struct inside. Flattening a struct, especially if it's in an array of struct, it really helps. And the third one, which is common, is a struct with an array at the end, a variable size array at the end. Most things that are messages and packets and payloads look like that. We have a struct with a bunch of fields, and then there's a byte array dangling off the end or some other field array. All 3 of these are very commonly used in C, and I don't really need to give you the use case. Just go read a bunch of C code and see that it's used all over the place. This is where speed comes from. And none of these can currently be matched in a Java world for speed. We can express every one of these relationships, and every one of them requires extra dereferencing and often breaks the ability to stream. So that's what we're trying to fix. The starting point for this is that we're trying to capture the semantics. We're trying to do this with no language changes or no spec changes whatsoever. And we're basically trying to express this as vanilla Java classes that'll run on any JDK that exists today. What we're doing is making it possible for JDKs to then recognize what the actual semantic contracts are and optimize for them, because with these new contracts, we'll be allowed to lay out things the right way, the way C gets to, because we tell it to. And ideally, or not just ideally, this is the harder part of the design, we want to make the vanilla and the intrinsified versions behave exactly the same way from a semantics point of view, and the only difference should be speed. Okay, think of this as the principal points for object layout. The model for this, for me, was java.util.concurrent, which pretty much followed that. If you think about it, it captured semantics that enabled fast concurrent operations. It did not have any language changes, did not require any JVM changes. How many of you have used the precursor to java.util.concurrent, which is the Dudley, Unioswego, Java 142 util concurrent stuff? Anybody here use it? Yeah. Well, you wrote the book, so. But that worked on a JVM. I mean, yeah, it had a little help, but it could work on anything. You can implement an atomic long compare and set with synchronized blocks. Not necessarily fast, not a good idea, but it works. It's semantically identical. Then when we had JDKs that understood it, we improved it, and that same thing is one x86 instruction, right? But the key thing is the semantics are defined. And then we moved those semantics into the Java namespace, and doing that allowed us to secure access both to the intrinsified stuff, but also secure legitimate access to unsafe. Unsafe is the stuff that people outside of this group should not be using. And it's stuff that people inside JDK and JVM implementations have to use. Unfortunately, we've made the mistake of exposing it outside of the base, outside of the boot class path stuff. But it's unavoidable that we need to use it for certain JDK things. So let's look at these 3 constructs, and structured array is the main one. I'll touch a little bit on the other 2. So what is a structured array? It's basically a collection of objects of type T. And it's arranged as an array, so you can do a get on an index. That's basically it. Now, the collection is immutable. There is no put. And it's also instantiated using a factory, not a constructor. I'll touch on that a little bit later. So you can make a new instance for a certain class with a certain length. That's pretty easy. All the elements will be constructed at instantiation time. So when you make an array, everything in it will be constructed right there, because you can't put anything in later. So there's pretty elaborate support for construction, whether it's a default constructor or some constructor args, or even the ability to give a provider that says, given a given index in the array, here's the constructor and the args I want you to call on element 17, because it has final fields that I want to initialize to something that's related to the index. So we've worked through the various things people might want to do in order to construct this. Any Java constructible class could be put in a structured array. That's why we worked hard to make constructors work. Liveness is another obvious and very important aspect of this. We started off looking at this and saying, well, other runtimes have this too, so liveness should obviously be if you point to the middle of an object that's big, then the object is alive. That's what other runtimes seem to do when they have arrays of structs or when they have references to inner fields. And then we had a breakthrough when you realized that we have real objects in there. We're not trying to save headers. We're not trying to change the quality of the objects. Quite the opposite. We want any constructible Java object to be in there, and we want to be able to pass it to other things that don't even know that it's in this weird thing. And real objects have their own liveness. They don't need to keep anybody else alive. In fact, collections keep their members alive, but don't expect their members to keep them alive. This is just a collection. It's got no other meaning, right? So normally if you want, you could have an explicit reference back from your element to your linked list, and that will keep it alive, but you don't have to, right? Just the fact that you're in a bag of something doesn't mean the bag is alive if you're alive. And that actually makes things very nice because it's very natural. Under the hood, obviously, anybody that wants to implement this in an optimized way will want to keep the collection as a container all together, flat, so we could do all the nice access and math. But that's an implementation detail. By the way, this really helped the vanilla implementation of Java, because figuring out how in a vanilla Java to make an element keep its container alive was a complex thing. When we figured out we don't have to do that, everything became easy. So what are the benefits of this liveness? As I said, it's just a collection, and there's no special behavior. It's natural. People that will see it as a collection don't care about the speed, understand what it does intuitively. It just happens to be fast. In addition, you can take any object that sits in any of these structured arrays and have it participate in any other object graph you want to. You can use hash maps to index the array. You could put it in linked list. It could be an entire graph on its own. You could do whatever you want with it. It can be locked. It can have identity. You can pass it to some 5-year-old library that expects to do that to objects, right? Everything that can handle a Java object can handle something that would sit in a structured array. And that's a powerful thing. It means that we have compatibility with those 10 million developers and their history. And it's natural, as I said. The other interesting thing is it's very easy to implement in a JVM. And I'm doing a workshop tomorrow with some details, but it is fairly easy to support what's needed for this in a JVM as opposed to trying to keep containers alive because their elements are. Some more features of structured array. Well, we're in 2014, so the indexes are long. We don't need to explain why. It is a multi-dimensional array. It already has support for that. So elements that are not leaf elements are themselves structured arrays. So a 3-dimensional structured array is a structured array of structured array of structured array of element. Did I count right? I think. What that means is you can have, say, a row column kind of arrangement where the rows are indexed with a hash map. And the rows can individually stay alive without the entire table staying alive because somebody wants them around. It's a natural kind of behavior, and the fact that every level in the array is in itself just a full-blown array object is very convenient. It's subclassable. So you can add your own fields at the beginning. You can add color to it. You can add animals to it. You can add whatever you want to it. And that supports some very useful styles and optimizations. And I'll get to those tomorrow, probably. It's also not constructible. That's a very important feature that's really forced on us by what's expressible in a JVM. We need to make these things, and they have variable sizes depending on how many elements and what their size is. We unfortunately don't know those things until the constructor gets called. But in Java, if you're going to new an object, you need a fixed known size before you call the constructor. So we have a contradiction there that we can only resolve with factories. So we can't allow a construction of a structured array to happen. Now, did you notice the small contradiction here? Yep. Yeah. So yeah, I was waiting for somebody to say, wait, yeah. So there's an interesting solution to that. I might do a lightning talk on that today. It's called constructor magic. And it might be useful for people to apply in other places where you need both of these things, non-constructible but subclassable. The contradiction is that if you're subclassable, you have exposed a public constructor. So how can you do that without allowing construction? And it works in vanilla Java and in intrinsified things. What do optimized implementations look like? The main thing an optimized implementation needs to do is deal with this new concept on the heap of a contained and container object. So we have a relationship between two objects, and we want to keep them together. So a structured array here is a container of elements that themselves could also be containers if it's a multidimensional thing. A contained and container objects are just regular objects. This is just a note, a hint, a requirement for how they're laid out. And given a contained object, there is a way for the JVM to figure out what the container is. There are various ways to implement this, everything from a back pointer to object start arrays to B trees that map these things and variations on all these. The implementation itself is not very important, but they're fairly easy to do. If the GC ever moves an object, if it ever reaches a contained object and it needs to move it, it's supposed to take the entire container with it. Because the basic assumption in an optimized implementation is that this thing stays flat anywhere it goes and that it's valid to do dead reckoning into it. And the layout will stay, ordered the same way. That's the main thing that an optimized implementation needs to do from a layout perspective. It affects mostly the garbage collector. And it appears to be very simple to implement in all the garbage collectors that we know of right now in OpenJDK, in Zing, and we think in others as well. So this is not a hard thing to do. It doesn't mess with the normal garbage collection behaviors, doesn't add any passes. It's just a nice, easy side effect, and we'll talk about it tomorrow. More on the implementations, the streaming quality and the streaming speed comes for free just from layout, right? Will be flat. If you stream through it, it'll be in the right order and addresses, so you don't need any optimizations for that. The dead reckoning parts do need some optimization support, some compiler support. And the reason for that is that while we can avoid dereferencing, we don't actually go through the referencing pointer, this is roughly what the address calculation looks like. We take the array, we add the array body size, then we multiply the index by the element size. But the element size and the body size are not constant. The element size is whatever element size my instance of a structured array has, which could be a variable and I need to get it, and effectively I have a data-dependent operation in my address computation, right? So instead of a dereference, I have something else, but it's still data-dependent. Luckily, we can optimize that. And there are optimizations for these that look a lot like class hierarchy analysis and inline cache optimizations do for invocations. So if I have a leaf structured array type that has exactly one size and I can analyze that in the world, I know what the element size is, I don't need to load it. And even if I can't prove it, if my code has only ever seen one element size, I can compute based on that element size and check the type. And that changes from a data-dependent operation to a control flow operation, which the CPUs know how to speculate past fairly well. Both of those optimizations allow us to reach close to or identical speeds to C arrays in access speeds because of it, even for dead reckoning. The place where the dead reckoning really matters are when we don't have a stream, when we're doing single shot or truly random access operations, like a hash map or other things. Okay, so I talked about structured array. I'm going to pause here for a second. I want to see if there are questions that were raised. How are we on time, by the way? We started a little late. Okay, so we're good on time. Any questions about what I said structured array so far? Yeah. Yeah. If you take an object and put it in your structured array, well, remember what I say, you can't do that. There is no way to put an object in structured array. Now, what you can do is create a structured array, and then you can take one of the objects there and also put it in something else. But there is no put operation. And the same applies to an array of struct. You cannot take struct number 17 in an array and put it in another array. Struct number 17 in an array is a range of addresses in the array. So that quality is where we get the speed in the layout from, and we maintain it. So you can't have two structured arrays that share objects. That's just, you can't make that. But you can make a structured array and share its elements with any other collection that does have a put operation. And there are many, many of those. Yeah? So the question was, do we support different layouts other than one after the other? Right now, no. And I think that the various work being done in Arrays 2.0 for interesting layouts, sparseness, growness, column versus row, all those are very good things that as they're developed, I think we can also apply here. It shouldn't contradict anything there. And the same concept could probably be applied on both. But right now, it's just a straightforward, top-down. A multi-dimensional array is an array of array of array. And remember, you can effectively dead reckon into it because you have the lengths, and at least in a loop, you could do that very well and stream through it, right? You're not pointer hopping in doing it. But for the layout that I think you're asking, because you might want to mesh your columns and rows selectively, when we figure out what those look like for other things, I think we can also extend them here. Okay, so I'm going to continue and take the yeah.
So you can't actually use this to make arrayless or arrayless and half-map will not use this.
Right.
Be able to add elements.
Now, this is not an array list. It's not a hash map. Neither one of those have the speed qualities that C has, and C doesn't have fast array list or hash maps, except for the ones that are implemented with, kind of the other kind of linking. But array lists and hash maps have their own separate qualities. So we expect this to be used in the places where an array of struct would be used. The natural places where those would use. An example would be a large ring buffer of messages, right? Remember, these are potentially mutable, very likely mutable structures. In a situation where what you're doing is putting something with two fields on it, there will be overlap between this and a value type, for example, and you would want to choose which one to use, because if it's truly immutable, okay, great, and even if you are replacing them a lot, then still, it's a two-field thing. You could do them either way. But in situations where you have where it is naturally mutable, see, all the usage patterns for structured array, for arrays of structs that I know of are very mutable. Those same patterns can now be done in Java without loss of speed, as I do. Okay, I'm going to continue to the next ones and then take questions at the end, so we'll eat up the time right. There are two other forms we talked about. Structured array is pretty well baked. I mean, it's not done, but it's fairly mature. We beat it up a lot. These other two are, we left that for later. And in the source code on ObjectLayout, you can find them, but I expect there to be a little more morphing of them. The first one is the struct in struct. We're calling that intrinsic objects. That's the current name I chose for it. Intrinsic in the English word meaning. It's intrinsic. Object X is intrinsic to object Y. Right, it's right there. The proposal for that is to basically use factory-based instantiation of final fields and it'll look something like this. I don't expect the syntax to be exactly this because there's some loopholes in here. One of the goals, as I said, is for it to be impossible to do something in a vanilla Java implementation that is different from the intrinsic behavior. And there are things you could do here that would have a difference. The reason this is a factory, by the way, not just a final field equals something, is what if you'd said final field equals something that's already somewhere else? Right? I can't let you do that because I can't intrinsify that. So we have to restrict the semantics to the ones that an intrinsifying JDK can match, right? But I expect it to be close to this. It might be some intermediate state where you create a static thing that makes the factory for you so it can't be faked. So that's one. And the idea is, they'll just lay out inside each other. This is not a variable size object. It's just figuring out that object Y is large enough to contain object X. They're both proper objects. They have headers. You can have references to them. And Y will be a container of X, just like structured array is a container of its members. From a garbage collection point of view, these are no different than a structured array. They just need to know how to walk on the inside. You have to deal with this. In this, one of the challenges is that we have to deal and survive the situations where reflection overrides the private and final behavior of fields. Which is why what we probably will end up doing is retain the reference from Y to X. So there will be a reference right there. This O will actually be a reference, but X will also be inside. As long as the compilers can prove that nobody has broken the rules and stored into this final field, we can legitimately dead reckon from Y to X. But if somebody anywhere has stored into the final O somewhere in the universe, then compilers will have to throw away that optimization and just do the regular old thing of following the references. It's an example of how you could sort of play the game and gain the optimization, but still survive the fact that somebody might mess with it. The struct with an array at the end thing is naturally, from a semantic point of view, it's naturally captured as a subclassable array. That's because we're in a single inheritance world. There needs to be only one array at the end. Subclassable arrays give us that one array relationship. So your class is what the fields are in the struct, and you can keep growing them with subclassing. And the array is logically at the end, probably physically at the end. But you have that relationship and that benefit. ObjectLayout already has classes for each of the primitive array types. There are primitive long array, primitive double array, etc. in the vanilla configuration, and we'll intrinsify those. A vanilla implementation is trivial. It's an object that has a long array, right? In intrinsified, it'll flatten that out. And then we also have a reference array of an arbitrary type. This is a good example where the fact that it's generics and there's erasure creates all kinds of things we wish were different, but that works. And then structured array is already subclassable, so it actually captures the struct with array of structs at the end, just as well as there's just array of structs. Yeah? So the question is, can you intrinsify one of these into another struct? So one of the areas I still haven't gotten to is how to deal with intrinsifying variable size things, right? Now you won't be able to intrinsify a variable size array into another object, but the common request is, can I intrinsify a rectangle with 4 points into something? It's 4, it's not variable, it's a fixed size, we can compute it. And again, this goes to how do we semantically capture that 4 in a way that you can't cheat. There are all kinds of tricks we're thinking of creating some sort of a static constant thing that is 4 and you cannot cheat with. Because if you pass me a constant, I can't believe that it's a constant. It might be 5 in the next call. So there's a lot of play around with how to capture something that will let us restrict the semantics the right way. But if we can, then you'll be able to do that. In the reverse, though, you can already, you'll be able to have a structured array of structs with a struct inside, right? A structured array of objects that have intrinsified objects in them. That would be a natural thing without that. And I'm hoping we'll figure out the part about how to do fixed size arrays within objects. I'm not sure. It's in the yet to be worked out category. These three are fairly well understood. For status, this is where we are right now. There's vanilla Java code for structured array that's up and working and has tests that's up on GitHub. This is all public domain code under Creative Commons 0. Again, taking a page out of Doug Lee's book with java.util.concurrent. That's how it was built. GitHub wasn't around at the time, but yeah. So you're welcome to go look there. We're looking for comments and input. It's, as I said, structured array itself is fairly mature, and the other two are still kind of a little more in flux. There is example code used, by the way, for the various structures in an examples directory, and I've had other people write code and examples for it. There are intrinsified implementations coming soon, both for Zing and for OpenJDK, and we will make the OpenJDK code available. And the idea is that we will look to start an OpenJDK project and later a JEP to solidify and capture this and argue about it. And then our aim is to add this at some point to some Java SE platform, hopefully 9, and we'll see what that means. A key point is the vanilla implementation will work on all JDKs. So you don't actually have to complete the speed up in order to add this, right? So as a summary, this is a new set of Java classes. The purpose is clear, and we're proposing that we move them into the namespace for Java SE over time. The reason to move them there is the same reason that java.util.concurrent moved. I want secure access to intrusification, and I want legitimate access to unsafe. Right now, I'm going to have to hack through to get to the unsafe the way everybody else does. But since I'm one of the people trying to tell people not to do that, you know. So basically, my take is if you're inside the namespace and inside the JDK, it's legitimate to use unsafe, and it shouldn't be for other people. So, you know, we should follow what we preach. This will work out of the box on anything. We're probably going to start Java 6 and above because people are still running 6. So the object layout stuff is not using language features above that. We are looking at how to make the APIs, say, Lambda expression friendly so that you could do either one. It's an interesting challenge on building an API that enables Lambdas but doesn't require them. It's a cool trick because you really end up wanting to use those nice default methods and interfaces, but then you can't use it with other stuff. So we'll see. I'm sure we'll work that out. So no new JVM behavior, no new bytecodes, no new language stuff. The go fast stuff is what JDKs will need to do. We'll contribute and take on the work of making OpenJDK do it. We're doing it for Zing. And anybody else that wants to do it should be able to do it fairly easily. But it shouldn't be required that you go fast. You just need to be able to support the class, and the class is vanilla and working. So that's it. That's it for today. Tomorrow we'll go into details of, more what does it look like? What are the specific concerns for JDK and JVM to actually optimize and intrinsify this? That's what the workshop will be about. Okay, how are we on time? Okay, so questions? Yeah, Peter.
What's the performance like if I don't have to go fast stuff?
I haven't clocked it too much. I do have a couple of micro benchmarks, but Alexei will tell you what, how much those are worth. They're not written in JMH, so but if you look at the implementation, say structured array, for example, structured array, in the case where you're not doing an array longer than you could do in an int-indexable case, it basically has an array of int arrays inside, but it has the first one directly accessible. So you're going to take the index, go down into a dereference to an array, and from there on, you're at the speed of an array. So it's an extra dereference for the vanilla case compared to a raw primitive array of the same thing. most collections end up with that same level of wrapping. So for example, if you look at a hash map, it has an array inside. You have to hop to get it. So I would say that the vanilla case is very similar in speed to what any other collections would do for if it had an internal array of some sort. No worse, no better. And then the intrinsified cases, obviously, we're hoping to get extra speed both for streaming and for dereferencing from that. Yeah.
In the optimized case, how much sort of cross-cutting concern does it introduce on new things that have to be represented in heap dumps and have to be parsed by dump analyzers, and how much new stuff does there need to really be sort of unsafe for getting it from elements of the array?
So those are two questions. The first one was in optimized case, how much do we need to look at tools and heap walkers and dumpers and what they need to understand? The beauty of this just being object is the answer is nothing. Because these are just objects. The relationship are exactly the same for vanilla and not. They are the same objects. They look the same in the heap, even in intrinsified case. There's just this extra knowledge that they're contained within each other. If you wanted to actually dump that, maybe it matter, but all you have to know is if you know you're an intrinsified thing, you know that that's flat. That you know that it's flat. You don't have to be guessing that it's flat. And if it's vanilla, then it's the layout you have. To the other question you had, how much do we need to add? Right now, we've identified 8 JVM API calls we need. We're adding those to unsafe right now. That's probably the straightforward one. Of those, one of them is needed for the fast path, the get operation, and the other ones are for construction and instantiation. And we're trying hard not to make them specific to any class here. So for example, we need a call that tells us what the size of an object is. We also need one that tells us what the size of an object when it's contained and when it's a container, because those might all be different depending on implementation. The one we need for speed is the one that tells us, given an object and an offset, give me a reference to that offset that is actually a reference. It's basically a cast of a long, but we needed to go through an unsafe in order to be safe for the JVM to do. One more? Yeah.
So the intriguing invariant of the garbage collector is that if the containing object is promoted or tenured or has some transition, then all its elements will be promoted.
Yes. The assumption is all movement happens together for the outermost live container, if that makes sense.
Yeah, so aren't there, not DC expert, but aren't there some DCs where you can't know you're going to promote the whole thing until a long time after you've decided to promote any of its elements? So how do you go back and is there some clever way you can know in advance whether you're going to promote the container or not?
So the answer is probably no. I'd like to think that I'm a GC expert, but we looked at the various collectors. Anything that has a mark sweep, mark compact component to it is a two-step operation, and you kind of have the answer when you get to it. The copy type single pass collectors are the ones that hit the thing you're talking about, because during the collection you can end up encountering a member before you hit the container, right? And you don't even know if the container is alive at that point. And the answer is simple, move the container. So if you get to an element and the element indicates that it is contained, which in a copy collector it will be contained because it was allocated that way, then you move the container and you keep doing it, then the container is, it will be promoted. It'll die in Olgin.
But then you also have to recopy the containees, don't you?
You move the container with everything in it. That job is actually simple. You're just picking it up and copying the whole damn thing. It's flat.
Sounds like you're creating garbage during garbage collection because you have to evacuate the provisional placement of the containees before you got enough container stuff.
You don't have to evacuate it. Effectively, when you reach at the point where either a copying or evacuating collector or compacting collector will reach something it needs to move, it's inside a flat area, it'll find the outside of that flat area and move that whole area over. Then it just needs to do the closure over it to close the pointers, right? But it does mean that, for example, in a new gen, if you made a structured array and only one member survived, the structured array and its members will make it to all gen before they figure out they're dead, right? Which, if you think of any, like, that's much better than what C# does with it, which is it will be alive forever as long as this one thing is alive. Right? So in single pass collectors that could arrive at the member first, the collector will end up considering the entire container to be one thing that it moves. And at the point where you reach a collector that knows the difference, then it'll die. Yeah. But that's actually kind of part of what I was going to cover in detail tomorrow, but we'll do that again. And yeah. Last one, or do we wrap up? Yeah. Copy part of the array? So the array is the collection, to be careful there, is either alive or dead. And if it's alive as a whole. There is no, right now there's no chopping or expanding. And again, there's Array 2.0 proposals to do those, and we might be able to do those here too, virtual memory tricks and the rest. There is a copy operation. There's actually a shallow copy support that will support a range. We put that in there because the guys who want to use it want it. I haven't quite seen how useful or not it would be, but it's the typical thing is I've got a large array and I want to copy a part of it. And that's just iteration. I mean, you could do it, you could write that yourself. You construct the structured array, and in the constructor provider you give it a constructor that for every index picks up the object you want and copies it. That's what the copy constructor for a structured array actually does. It's just, that's assuming that the elements have a copy constructor. And if they don't, then I can't copy them for you, right? You do it. Yeah. But it's really up, think about it this way. You're constructing a structured array, and you can provide the way to construct any element in it, including not copy, but individually copy the fields you want, right? And you could do it in a way that tells you what the index is or what the multidimensional index is to that. So if you need some arbitrary logic there, you have the place to put it in. Okay, I think we'll have more time to talk tomorrow. But thank you, everyone.